that. Assalamualaikum everyone. It's not that hard. It's trying to remember you. There have been Assalamualaikum colleagues online. Good morning, good afternoon. They've been traveling God all over. So last night I came after visiting 7 countries. I was in Turkey, then Russia. God, and then I was in China. I was in Iran. I was in Bulgaria. I was in Bangladesh. Back home. Only for a few hours and leave for some about tonight in China. Okay, so
Slide to change it here.
I think I keep changing everything. So I'm sure that my colleagues have actually recapped what we have been discussing. Problem with NMR is that it's just like a slipping thing, you know. I mean, you have something in your hand, you try to hold it. If you don't hold it very strongly, it just slipped out of your hands. NMR is kind of that thing also. But I'm sure that you are the smartest group of people, the most brilliant one ever. And with that, I'm pretty confident we able to reconnect what we were discussing. So till then, till my laptop is connected, let me remind you that we are in the world of micro, little, tiny nuclei, which contain neutrons and protons, and they are collectively called nucleons. And they have a property called spin, provided that either proton or neutrons are in odd number. If they are in even number, they are totally paired up, and they are NMR silent because spin is 0. But when any one of them, I mean neutron or proton, is an odd number, they are unpaired, and as a result of it, they have a property called spin. So non-zero spin, nuclei with non-zero spin are the NMR active one, and nuclei with zero spin are NMR silent. So we are now in the world of NMR active nuclei who can talk to us. They talk to us, they whisper, they speak, they have music, they play, they dance, and everything. They do everything in a very little micro world. But for them to do all that, they need a stage. And that stage is applied magnetic field. If they are not in the applied magnetic field, they're still dancing along their axis, but they are dancing everywhere. So you don't really know it, look a crowd. But when you place them on the stage under the applied magnetic field called P naught, then they start in a very organized manner. They, number one, they divide into groups. But I've never had, in last 7 countries, I've not seen any dance. So please don't think that I've been in the mood of dancing or whatever. But they organize themselves. If they are spin half nuclei, they become 2 groups. One aligned to the magnetic field, the other is opposed to the magnetic field. And this difference in energy is called Zeeman effect. And this difference in energy is the one which eventually lead to the absorption of radio frequency, because that eventually creates a resonance. So remember that NMR is all about nuclei. NMR is all about non-zero nuclei. non-zero spin nuclei. NMR is all about applied magnetic field. NMR is all about the effect of applied magnetic field on nuclei. And when you apply a magnetic field, two things happen. That they divide into various quantized states, spin half nuclei, or either two states or more states or whatever. But also they start a new action called Larmor frequency. This precision around or opposed to the magnetic field is called precision frequency or Larmor frequency. Larmor was the name of the person, Joseph Larmor, who first predicted such action. In an NMR spectroscopy, your task is to measure that precision rate. How would you do that? That is the challenge. Okay. How would you measure the precision frequency? Is the challenge for you to handle. And if I move through, this is what I showed you, that this is the axial moment. And I told you that this spin, spin odd, this odd mass or atomic number. And I also told you that this is the state without the magnetic field when there is no applied magnetic field. But when there is an applied magnetic field, then you have two or more quantized states. And this is the precision frequency which we have discussed. Precision frequency. You see, often you think that this is all about Assalamu alaikum. My distinguished colleagues, Her Excellencies, and all that. So, you think of it. I was actually thinking, yes, last night when I was traveling, we keep just so much of emphasis on nucleus, and we often ignore electrons, right? And we say there is no role of electrons in NMR spectroscopy. The fact is, NMR electrons play extremely important role. If there was no electron, there was no chemical shift difference. If there was no electron, there was no difference in precision frequency. More nuclei, less magnetic field, that's shielding. Less nuclei and less electrons, more precision frequency, they shield. So electrons play very important. Electrons are critically important because if there were no electrons, all nucleus of an element have the same Gangler shift. So remember, never ignore electrons. Respect them with core of your heart, right? Remember, electrons are very important for you in your life, in all of our lives. Okay? So always remember that electrons are critically important, and that NMR electrons are the one who define the utility of NMR spectroscopy for chemists. If there was no electron factor, all nuclei of an element must have feel the same magnetic field. Only when they are in more, because electrons have their own counter magnetic field, they're also spinning charges. They have their own counter magnetic field. They oppose the applied magnetic field, and the effect of applied magnetic field for different nuclei are different, and that is what defines the precision frequency. Now, remember that I also told you about gyromagnetic ratio. Gyromagnetic ratios, this one, that are critically important. NMR is all about specificity. You know, in your compound, you can have hydrogen, you can have carbon, you can have oxygen, sulfur, nitrogen, so many elements. NMR is the only technique, and I say only technique, which can detect one in the presence of other without interference. IR, no distinction. You get a spectrum of the entire molecule. UV, no distinction. You put your compound in solvent, you get the spectrum. Mass spectrometry, no distinction. You put them into mass spectrometry chamber, they ionize, and you get everything. In NMR spectroscopy is the only technique where you can detect proton without interference of carbon, hydrogen, nitrogen, oxygen, everything. You know the reason? Because no, not odd, not odd. Magnetic gyration, because they resonate at different precision frequencies, and you can tune that effectively. It is like copper, steel, any silver, gold, and different elements. In the presence of applied magnetic field, they would all have a different reaction towards magnetic field. Similarly, their magnetic gyric ratios are different. So carbon, hydrogen, proton, nitrogen, sulfur, all elements of periodic table, they have different magnetic gyric ratio. And magnetic gyric ratio is experimentally measured. Though you can calculate that, but it's experimentally measured. And this is the reason why you can selectively detect one in the presence of the other. Okay? And this is the only technique, NMR spectroscopy is the only technique which is so specific that you can detect one in the presence of the other. And this is the reason. This is a constant which is called delta, magnetic gyric ratio or gyromagnetic ratio. Thank you. So if I am disoriented, think of dozens of flights which I have taken so far. Okay, so magnetic gyric ratios are different. The proton has gyromagnetic ratio 267. Deuterium is 41. Carbon 1367, about 1/4 of that. Fluorine is 251. And as a result, you remember with precision frequency is directly proportional to V naught. The more stronger the magnetic field, the more this dance would be, right? And the proportionality constant is this much. This is the difference. So precision frequency for every element would be different because every element has a different magnetic gyric ratio. And this is the reason, if you wish to match precision frequency in quantum physics, you need to match precision frequency in order to absorb radio frequency. And in order to absorb radio frequency, you need to know, you need to tune your radio frequency Therefore, this radio frequency, this precision frequency, is different for different elements. Precision frequency is different for different elements, and this is the reason that you can measure them specifically. Understood? If not, is the fundamental concept. If you don't right now understand and comprehend, please discuss this with me. Okay? Because this is the key factor. This is what make NMR uniquely distinct. This is my coffee, please. Just waking up. If I don't drink coffee, I'm like a zombie on full moon night. You know about zombies and full moon night? There are two types of people. There are zombies and there are poets, शायर. इन दोनों को कुछ होता है full moon night. Okay. So this is a fundamental cause. Let me define you again. Every element in periodic table react differently to magnetic field. No, they're different, right? Therefore, they have a different magnetic Garrick ratio. And when they have different magnetic Garrick ratio, you know, this one is same for everything. You have the same equipment for all elements with same magnetic field. Only this is different, right? And when it is different, you keep placing this magnetic gyromagnetic ratio in the equation, and you will know the precision frequency. So you keep changing this, and you would have precision frequency for every element. Now you tune your radio frequency to that one, your Radio Pakistan. You tune that to Radio Cairo, Radio Khartoum, right? Or Radio Sana, or Radio Yuande. Okay. So you keep tuning it, right? And that is the reason that you can detect an element without the interference of another element. I'll take you to another difficult journey, even for the same elements, hydrogen or carbon, same element. We're not talking about different elements. Same elements. This is same. Let's say assume hydrogen. This is same. What is different? Absolutely, you know. So you learn this beautiful concept which you cannot really learn from 50 different books. You keep reading it, and nothing will happen. So if you have hydrogen, which you're trying to detect in a complex molecule in which you have 30 different hydrogens, right? For all of that hydrogen, the magnetic Garrick ratio is naturally the same. No difference. What is different? And why this is different? Because of a little brother electron. You know, because this little brother electrons gather around sister nuclei and shield her or de-shield her, right? And as a result of it, the precision frequency for different protons of the same molecule would be different. And that is the reason you would be able to differentiate based on chemical shielding, the chemical shift. Chemical shift is the observation of chemical shielding, right? Understood. I would like to spend 2 days on this concept. And if you today, at this moment, understand that concept, it is that poetic moment when the results super there. Yeah, very, very. How many of you are poets? I love that you are a poet. Yeah, I know. You're a poet. You do shairi in Arabic, right? No?
I share.
Yeah, I knew about it. Yemenis are generally shy. Yemenis are very cultured people, you know. I learned that Yemenis have actually moved all to West Africa and Mauritania. Is this correct? People of Mauritania are Yemenis. Yeah, but they are not Yemenis. They claim that they are Yemenis.
Yeah, Yemeni is the origin of Arabic.
Are you sure that you are Yemeni as well? Your Egyptians claim that this history from Europe or Arabia. Huh?
I am Arabic Egyptian.
But the origin of Arabic.
Now we can discuss except NMR in the region of Arabic. Okay, so now you understand different elements in periodic. Number one, my question was if an isotope, the abundant isotope of a nucleus, if you want to detect the NMR of an NMR silent element, what you would do? At least one of the isotope, most likely would be NMR. Okay. So it means that theoretically all periodic table is NMR can be detected by NMR because at least one isotope would be. For instance, carbon 12 is NMR silent, but carbon 13 is NMR active. So oxygen 16 is NMR silent, but oxygen 15 is NMR active. So it's possible. Now it means that theoretically every element can be detected. Now the second question is, how can you specifically detect one element in the presence of the other one in a molecule? Because your molecule can contain many different types of elements. How can you detect carbon in the presence of hydrogen or nitrogen and oxygen without any interference? Because of this. Since they are different for every element, you just tune it. You tune your radio, right? Radio frequency. Match it with the precision frequency. You have nothing but that. No, nothing else but that element. No interference. If the same element, this one is same for all nuclei of the same element. And this would be different because naturally they would have different kinds of nuclear electronic shielding, and B naught would not be felt by all nucleus of the same element as they will not be same. The thrust of B naught would be partly broken by the counter magnetic field of electrons present around the hydrogen nuclei. So this is going to be different. When this is going to be different, this is going to be different for different protons. And you would be able to see them on the spectrum. The more electrons, less B naught, right? Or shielding. Less B naught, less precision frequency. Less precision frequency, shielded. Okay. Less electrons, more B naught, more precision frequency. D-shape. Okay. It's called upfield region, called downfield region. So this is the fundamental basic theory of NMR spectroscopy. Now, I want to ask you a question. How to measure this? Imagine that you are sitting somewhere in a laboratory in Berkeley California, and somebody told you that Isaac Rabbi has talked about a precision frequency which was defined by Lama a long time ago. How would you measure it? Because this precision frequency is the one which can tell you about electronic cloud, microelectronic environment, and that can be related with certain features. How would you measure it? Why you need radio frequency? I mean, if you could have measured precision frequency directly, there was no need of radio frequency. Think of it, if you can measure radio precision frequency directly, what is the need of radio frequency? Problem is that you cannot measure the precision frequency directly. You know why? Because you cannot place detector vertically on top of a magnetic field. Magnetic field is in thousands of hertz. It is in megahertz. Precision frequency difference is in hertz. You would never be able to detect the stream in the presence of a river, right? So you cannot place detector on top of it. You need to have a detector on the side, perpendicular. It means you need to bring these to. So this is the reason why you give a radio frequency and you absorb radio frequency. And when you absorb radio frequency, you indirectly measure precision frequency, because only those radio frequency would be absorbed which match. Absolutely. Remember this quantized in quantum physics, the absorption of energy would only takes place when they are of the same frequency. So if it is the precision frequency, the radio frequency should also be matched. Okay. So when you measure the radio frequency, you measure precision frequency. Okay. That is the reason why it's called resonance. So what is Raman frequency? What are the factors on which Raman frequency of nuclei depends? Now, this is a question for you. What are the factors on which Raman frequency will depend? And these girls will give you money if you answer with their signatures. Yeah. They have been getting it since long. Yes.
It depends on temperature in the environment of electron.
Electronic shielding. Okay. One.
And second one is magnetic derivative.
Okay. You have reached to 50 rupees, and what else? There is one more important factor. I've learned that.
Effective magnetic.
Oh, effective magnetic field, you already told. Electrons. Magnetic field. Because magnetic field, be effective is a subset of magnetic field. Okay. You get 100 rupees, I think you get about 8 samosas, small. I learned that they are quite expensive now.
No.
Yeah. Very sad. Samosa inflation is a major problem, national problem. These girls, all of them, they take samosas. Okay. I like it also, by the way. Now the second question. What was the second question? What is this going on? Okay. If I give radio frequency perpendicular, what will happen? Give a radio frequency, my radio frequency oscillator is here. slowly increasing radiofrequency. It matched and it, so I record absorption. So this is the radio frequency. This is the radio frequency which has to be matched with precision frequency. Again, a question. Do all nuclei of the same element will resonate at the same Lambda frequency? No or yes? The physicists thought they would all resonate at the same frequency. For them, hydrogen is hydrogen. How would you assume that I am a physicist and a smart one? Exceptions. Anyway, so tell me, how would you convince me that hydrogen would resonate differently? They have a different procedure. Over to you, Adil. Adil is from a place called Bani Suef. If you travel from Cairo, you will find this beautiful city where you would have people in Mercedes and also donkeys. So you find a very interesting place. When I saw someone was driving Mercedes, then I saw someone was just in next to him. He was on a donkey and he was driving donkey by just pushing his leg. That was the first time I actually knew that how donkeys controlled. Okay. And that has helped me in my institution in Islamabad, not yet. Okay. Sorry, should not be recorded. Okay, so yes, Arvind, over to you.
Because of different different environment, the absorption, the effect of contact.
Over to you, Sheikh. Please share that.
Because of the difference in different environment, so the way it will be different. So they give different.
You're reading it from here.
No, I understand.
What are the factors which affect magnetic field, on which P factor is depending? Also some other factors which we will discuss. Thank you. You get about 100 rupees also. You know, the easiest would be 100 Tuman of Iran. In $1, I was in Tehran, the beautiful country of ours, and in $1 you get 1.4 million Tuman. Would you like to have man or piece? Yeah. Okay. Anyway, so it's beautiful that we have this now understanding that be effective. That is important. And what the energy is very different. The energy difference between, let's say, dipolar nuclei. Dipolar nuclei are the one in which you have spin half plus and spin half negative. Quadruple nuclei are the one in which you have more than two quantized transitions. So these are the two states in dipolar nuclei in which transition takes place. Okay. The difference between the two energy state is dependent on what factors? The difference between two energy states. Because it has a lot of bearing on NMR spectroscopy. The difference in two energy states or more energy states quantized and steady state is critically important in NMR spectroscopy. It depends on what?
Applied to the for the shielded proton, the electron density scattered in
Nothing to.
Applied.
I mean, the difference between two energy states. Uh, you're okay.
Applied limit.
I am convinced that you. Okay, the difference between two energy states. Amina from Khartoum, please. Hmm?
Yes.
What? You guys are so intelligent. Never thought about it. Yeah, be effective. What else?
Relaxing.
Shielding is directly be effective is direct. It's the manifestation of shielding. Be effective is because of shielding, right? You know. What else? I'll make it feel. What else? The radio frequency is nothing to do with this. Radio frequency eventually is transit between them. Right now we're talking about the stage. Okay, but good guess.
Then we have Excel for states.
It also depends on magnetic gyric ratio. Always remember, it's not mentioned here, but magnetic gyric ratio is also very, very important. For every element, the same NMR will give you the different energy state. Now, let me ask you a $1 million question. It's only in literal sense. I don't have $1 million. I'm not giving you $1 million. I'm just asking you a question. Okay, the question is, what is the effect of difference energy on population? Population in two energy states. To recap, so I told you that except NMR spectroscopy, there is no other technique in which you have both energy state populated. In all other spectroscopic techniques, either it is down or up. 100% down, electronic transition, 100% up, vibrational transition. It happens everything, you know. Either electrons are scattered in X-ray or not scattered in X-ray. Everything is just 100% zero or 100% up. Okay. NMR is that very interesting technique in which you would have 1 million here and 1 million minus 2 in the high energy state. Population, the both energy states are populated. And the difference is only tiny, which is called Boltzmann distribution axis. Boltzmann was the first one. He didn't really mention about NMR spectroscopy. He was talking about generally the weak systems in which both energy state can be populated. The difference in energy, the difference of population in that two states is only 13 in 1 million. So if low energy state has 1 million 13, the high energy state would have only million. Okay, the difference is only very tiny, which is called Boltzmann distribution axis. Think of it. Such a beautiful concept. And that tiny little difference is your NMR signal, because this is the one which will absorb. Right? This is the reason why NMR is a physics of weak forces. Okay.
absorption, cooking, then dumping of electrons with energy fields and depend on temperature. Does it affect?
Yes, it has a tiny effect of temperatures, but not a lot. Because at high temperature, there are a lot of other factors take place. The ambient temperature difference, slight temperature difference, there is an equation also in which there is a slight temperature difference, which can make a very little difference in population, but not a whole lot. Now, yes.
Now, you said we have 12,030,000 nuclear, and we apply xenon. Xenon will be in the alpha state, or no, in the beta state. 30 in the beta state. Only
This energy state are only created when you apply magnetic field. Remember, there is no energy states without applied magnetic field. Okay. The difference is only 30. It is only tiny. I gave you the example. I don't know. To be honest, the difference is just so tiny that they say that if there is 1 million in both, there is a difference of only 30. Only 30. Now, question.
but the NMR only meant only the 30.
Yeah, because
What about the
the absorption from one energy state to the energy state would be only the one which will transit, right? The population, both energy states are populated. Radio frequency would only be absorbed theoretically by the Boltzmann distribution axis. So this population difference is absolutely important, critically important, and that everyone in NMR, the world of NMR, is trying to increase the population difference. You have more population difference, you would have more absorption of radio frequency, you would have a better signal sensitivity. So somehow, if you can increase the population difference, now from next lecture on, we will start discussing about how to increase this population difference. The easiest thing for you to think of, the population difference can be increased by increasing the V naught. Okay. When you increase the magnetic field, the nuclei which are aligned to the magnetic field and opposed to the magnetic field would have a greater energy difference. It's like a compass. You have a strong compass, and if you're trying to turn the needle from north to south, you need to actually have more energy of your finger moving from there to there. So the energy difference, when the magnetic field is higher, the energy difference would be higher also. It's directly proportional to the magnetic field. Okay? Delta E. Now, when there is a difference in in two states, why the population difference would be increased? $1 trillion question. There would be a $1 zillion question also. I don't know what $1 zillion, but I think this is called Gen Z. Gen Z language, you know? Okay. My grandson was trying to tell me. And he said, I'm just cooked up. I said, what happened? And he said, you don't know? And he told me that cooked up means that I was just so absolutely upset on that. And he often called me bro. I don't know why. I said, be disciplined. I'm your grandfather and you should really be respectful to me. I'm not your bro. Okay. And he was telling someone, you're a goat. I said, what is this? This is not on. He said, this is the greatest of all time. I don't know what is the language. So the next lecture will be in Gen Z language. Okay. So the difference, when there is a great difference in energy, the population would be different because the transition between them become difficult. Right? If the energy difference is like this, The nuclei are jumping up and jumping down, right? When they are like this, the jumping become low, difficult. And that is the reason that population difference increases. The first thing which people have done in order to increase the sensitivity of NMR as a technique was to increase the magnetic field. And this is the reason why they keep developing the stronger magnet. This was the first thing we have done, and I said, good Lord, this is a very expensive solution. It's a very expensive solution. You know, the equipment which you have seen in animal laboratory, each one of them is about $2 million, $500,000. Think of it. They're a very expensive machine. If you get a 1.2 gigahertz, 1200 megahertz NMR machine, this will cost you roughly about about 15 million USD. So this is not a very good solution for sensitivity, and that is the reason why people have developed new techniques and they got Nobel Prize in return of it. Okay, so to now understand that, what is resonance? Magnetic nuclear magnetic resonance. So far we have talked about nuclei, we talked about magnetic field, we learned what happened when they are placed in magnetic field, stage is set, they are ready to dance, and now you need to give them energy. Energy drink. What is the energy drink? You are drinking that, right? You need to give them energy drink so they start dancing. There is radio frequency. Radio frequency matched with precision frequency. This process called matching. And that is what you record. Okay. This is what I told you, but any guess of the difference in population energy of the two energy states? There's this tremendous factor in NMR and spectroscopy. In UV, that is roughly about 130 to roughly about 190 kilocalories. The difference between low energy state and the other for electronic device. Kilocalories, kcal. The difference between IR, the difference between the two energy states of vibrational and vocational energy of vibrational energy, stretching energies is roughly between 4 to 6 kilocalories. In NMR spectroscopy, the energy difference between two population states is 0.04 to 0.06 calories. And that is the reason transition takes place. You know, because the differences are so much. And that is what you're trying to measure. This is the reason why NMR was developed at the end and took so long for people to make this technique more acceptable. Okay, so this is the transition between low energy state and high state. In the absence of magnetic field, degenerate. Under the influence of magnetic field, align and position. When radio frequency applied, transition. Right? Absorption and transition. These questions are very important, and we intentionally build this question for you to keep asking these questions to yourself. So this will help you to understand NMR more profoundly. Now take example of of N14, our beloved nitrogen. Nitrogen is very important for people. Nitrogen is important because, entire protein chemistry, it depends on that. Structural biology, molecular biology. Nitrogen is also important for people who are working on heterocycles, synthesis of nitrogen-containing nitric acid. It is also very important in samples of various kinds of small peptides, amino acids, and others. So it is a very important one. And any guess is going to be NMR active or not? Why is NMR active? Why you can't detect it? If it is NMR active, it should be detectable, right? This is the limitation I'm telling you, because even if they are NMR active, often the detection is, and this is 99.7, 99.6% abundant. This is the most abundant isotope of nitrogen. Speed point number one. These are 3 energy states, not 2 energy states. This is called quadruple. When anything is not dipolar, it's quadruple, right? So there are 3 energy states. Plus 1, 0. So they have these 3 energy states. Now you cannot really easily measure in your frame of mind. You think of align and oppose, right? That is the easiest thing for you to understand, such as proton, carbon 13, P31, F19, N15. But think of it, aligned, less aligned, more opposed, less opposed. There could be any spectrum of that. So these quanta states. Now these are 3 quanta states, 3 energy states. 2 energy states, we have seen the problem. The energy difference is so little. Think of it, 3 energy states. And train at 3 energy states, the transition between 3 energy states is such a mess. And when you have 5, 6, 7, transition is so different that Boltzmann distribution axis is just so little tiny that you cannot measure it. There is no equipment so far developed which can measure such a small little difference of energy between more than 2 quantized states. Okay, this is the reason why it is rapid realization transition between 3 energy states, or 5 energy states, or 6 energy states, or 7 energy states. So as a result of it, nitrogen is not observed. It's only observed when it is quaternized. I will tell you something later about that. N15, on the other hand, has a spin half later. Its spin state is half, is 0.36%. It has a problem. It's only 0.36% naturally abundant. It means that though it is an excellent nuclei dipole, but it's not so easily detectable in natural abundance because of a very simple reason, that it is very tiny in its population. Population is also very different, very important. The population is just so, and that is the reason why N15 labeled proteins are expressed. Oxygen 16 is NMR silent. You agree? Oxygen 17 is NMR active. 17, sorry. NMR 17, oxygen 17 is NMR active. But it has a spin number. So how many states? So it has two damping factors. Two damping factors. One, natural abundance. And second, multiple nuclei of a mess. No, it is a mess that you have not the population in 2 energy states, but in 6 energy states. The transition and relaxation between 2 energy states are just so absolutely vast that you cannot measure it. Okay? Okay, I think there is another class at 10. So my apologies for, and my dear participants online, my apologies that I've not been being so regular, but I'm sure that my colleagues are actually taking care of you. Saturday would be an online class because I would be in Islamabad. So inshallah, we'll see. Allah Hafiz. Thank you very much. And people who got this beautiful reward of 100 rupees, please contact these guys because I don't have any money, right? So, okay, thank you. And Adil also there.